axis or a couple of complex conjugate poles close to the imaginary axis. So the dominant first order and second order system. So let's say we are given the specifications as settling time less than 4 seconds and peak overshoot less than 10%. The question becomes, how do we process this, right? So if we recall, the poles of the underdamped second order system are at minus zeta omega n plus or minus j omega d, where omega d is the damped natural frequency, and that is equal to omega n times square root of 1 minus zeta squared. Essentially, if we look at the settling time criteria, the settling time criteria is 4 by zeta omega n. That is basically 4 seconds. Now, that's less than or equal to 4 seconds. If you process this, we get zeta omega n to be greater than 1. And if we multiply by minus 1 on both sides, the inequality gets flipped. Why did we do this? Because if we look at this, I'm reproducing the below diagram. I'm redrawing it again, one step at a time. So if you look at the S plane, if we draw the vertical line passing through minus 1, please note that, minus zeta omega n is the real part of this pole of the complex conjugate poles of the underdamped second order system. Now, minus zeta omega n less than minus 1 means it is this region, okay, from a graphical perspective. So, what this inequality, processed inequality means is that if you and I are able to place our closed loop poles anywhere to the left of this vertical line passing through minus 1, we will satisfy the settling time criteria. I hope the physics and the mathematics become clear, okay? So, in other words, if we have the closed loop poles anywhere to the left of this vertical line passing through minus 1, we will have the real part to be less than minus 1. Then we are satisfying this criteria, right? Which is the settling time criteria. Okay, so that is the first step. I hope this is clear, right? Now, how about the second criteria, which is the peak overshoot, right? So you and I know that the expression for peak overshoot is this, e power minus zeta pi by square root of 1 minus zeta square times 100. That should be less than or equal to 10%. So then e power minus zeta pi by square root of 1 minus zeta squared should be less than or equal to 0.1. So we solve the equality, okay? So then we will come to the inequality. So if we solve the equality, we get zeta to be 0.5911. Okay, so that is the value that you and I will get. Okay, so how do we solve this equation? We apply natural logarithms on both sides, the ln function that we see in our calculator, right? So that's what we use, and then like we essentially go ahead and process the corresponding equation. Okay. So that's what we have. We have got from the second second criteria. Now this is only by solving the equation, right? But what about the inequality? Okay, so it so turns out that if peak overshoot has to be less than or equal to 10%, zeta should be greater than or equal to 0.59. Okay, because if you recollect. Even from a physical intuitive perspective, as the value of zeta increases, what will happen is that the peak overshoot will decrease. Okay, so that's what will happen as far as the system response is concerned. So consequently, zeta should be greater than or equal to 0.59. And if you recall, cos beta was zeta, right? When we did the underdamped second order systems, right? Now all the mathematics will come into play for a physical intuition, right? So if we take cos inverse of 0.591, that comes out to be 53.77 degrees. So if this angle beta is less than 53.77, then our peak overshoot condition is satisfied. So I hope this exercise tells us how to convert a physical constraint on peak overshoot to a mathematical constraint on parameters that you and I have encountered, right? Now, what is this angle beta? If you recollect, what was this angle beta in the context of underdamped second order systems?
Jai cos beta is equal to Jai, sir.
Yeah, exactly. But then, like, graphically, what was that angle beta?
J, like so basically J omega n and W basically perpendicular and hypotenuse. Base is I think minus J omega n, and the perpendicular distance is omega d.
Yeah,
So the angle between that two.
yeah. So graphically, beta is the angle made by the line segment drawn from the origin to the pole with the negative real axis. This is what it is, right? Graphically. So if I hope that is clear, right? We have recollected what was the definition of beta. So now, if peak overshoot needs to be less than or equal to 10%, beta should be less than or equal to 53.77 degrees. So what we do is we draw two lines which are at an angle of 53.77 degrees with a negative real axis. Okay, so both are at an angle of 53.77. So what it means is that physically, if all our closed loop poles are in this cone whose apex is at the origin, then our peak overshoot is going to be less than or equal to 10%. I hope the physical meaning or implication is clear, right? So from this exercise, right? So if you and I draw two lines which make this angle of 53.77 with a negative real axis, and we look at this cone, right? Then whatever poles are within this cone, if as long as the poles are within this cone, the peak overshoot condition is satisfied. Now we want both conditions to be satisfied. So what should we do? We want both settling time and peak overshoot. So how should I calculate the feasible region?
So we should put the other constraint also on the same graph.
So it should be the intersection of the two feasible regions, right? So the intersection of the two feasible region is this region, right? So it's like an open trapezoid. Okay, so for settling time, we should have all poles to the left of -1. For peak overshoot, we should have all poles to be in the cone. So if you and I get the intersection, that will be the region which will satisfy both settling time and peak overshoot condition, right? So I hope it is clear how you and I have identified a sub-region of the left of plane, okay, in which we want our closed loop poles to lie in order to satisfy performance criteria. All right. So I hope this example is clear. And as we go ahead, we'll be using such tools, right, to narrow down, like the ranges of controller gains, which will give us both closed loop stability and closed loop performance. Okay. So to summarize, in this example, what we have done is that we were given some, like performance criteria. We essentially took those performance criteria and came up with a sub-region in the left of complex plane where we want the closed loop poles to lie. And if all the closed loop poles lie in this sub-region, then we will get both closed loop stability and closed loop performance. Okay, so that is the idea, right? So please remember this. Okay, so any questions on this before we go ahead? Any questions?
No, sir, everything clear.
Okay, fine. So this is how we essentially convert it, right? So now what happens is that, like, how do we go forward, right? So we go forward now to control design, okay? So essentially, if you recollect, we are just recollecting what we already studied. We are essentially looking at the negative feedback closed loop system, right? And like we essentially we drew this block diagram representation this week, right? And then we calculated the closed loop transfer function as g of s divided by 1 plus g of s h of s, right? Then we essentially need to like look at the closed loop characteristic polynomial or equation, right? 1 plus g of s h of s equals 0 to determine the ranges of controller parameters, which will give us closed loop stability. And g of s h of s, we defined it to be the open loop transfer. Okay, so this is just a quick recap, right, of what we already discussed, right? So then if we go down and then we start doing some examples, right? So let's look at this example, set of examples, so that you and I will figure out how do we do this control design, right? So see, typically, from a very practical perspective, broadly, when do we need to do control design? Like because this is a natural question for you and me to get, right? So you and I want to stabilize an unstable system. So let's say we are given an unstable system and we want to stabilize it. Okay, so then we design a controller, or we want to improve the performance of a stable system. Okay, so we have a stable system, but then we want to improve the performance of a stable system. Okay, so broadly these are two situations where we design controllers. Now the point is, let's start looking at some examples, right? So let's start in very simple examples. So let's say we take a plant or a system whose a first order system, right? Whose transfer function is plant transfer function is 1 by s minus 1. We immediately see that the pole is at 1. So consequently, the system is unstable. Okay. So let us stabilize this plant using unity negative feedback. So if you remember unity negative feedback, unity feedback means h of s is 1. Okay. And then, we have unit negative feedback, right? So if I construct the block diagram for this particular example, this is our plant transfer function. Then what we have is a reference input R of s. Then we have unity feedback. We have negative feedback. Then we have the error signal U of s. And then we pass the error signal to the controller, and then we get U of s, right? So let us first try out a very simple controller where the controller transfer function from KP. Okay, we try proportional controller. So we go one step at a time. Okay, it's a very methodical process. Okay, so first we calculate the forward path transfer function G of s. It's CS times PS, which is KP times S minus 1. Okay, so then we go to the closed loop transfer function, which is G of s divided by 1 plus G of s H of s. G of s is KP divided by S minus 1. And then 1 plus G of s H of s is going to be 1 plus KP by S minus 1, right? So if we process this, we are going to get KP divided by S plus KP minus 1. Okay, so we take LCM and then cancel out the common factors and so on. Then for the closed loop transfer function, it comes out to be KP divided by S plus KP minus 1. Okay. So the closed loop characteristic equation is the denominator polynomial equal to 0, right? So it's going to be S plus KP minus 1. So here this is a very simple example. So we can straight away solve for the closed loop pole. The closed loop pole becomes 1 minus KP, right? For closed loop stability, what do we want? We want this to be negative, right? Because if there's only one pole, if we want that pole to be in the left of complex line, we want it to be on the negative real axis, right? So we want this pole to be negative. So we want 1 minus Kp to be less than 0. That's when this closed loop pole will be negative. So if we process this, we have Kp to be greater than 1. Okay. So through this analysis, what you and I have done is that, as we know, as we discussed even yesterday, Kp is a real parameter, right? It can vary from minus infinity to plus infinity. So what we have done is that by using the stability analysis, we have determined that for this system, to make the closed loop system stable, we need Kp to be greater than 1. Okay, so no other value, if we choose Kp to be less than 1, the closed loop system is going to be unstable. So this is a powerful design tool, right? So because it has sort of like, it has done two things. One, it has told us which values of Kp we should search it, right, to ensure closed loop stability. And more importantly, which values of Kp we should not feed to the actual system, because that may make the system unstable. In this case, Kp less than 1. Okay, so that is what we have learned from this example. Okay, it's a very simple example. Like, we'll keep on adding complexity as we go on. All right. Okay. So, any questions on this example before we go to the next one? All right. Okay. So let's carry on. Right. So now we go to a second order system. Okay. So let's consider a second order system where the plant transfer function is 1 by s squared minus 1. Okay. So the poles are going to be at minus 1 and plus 1. Okay. So obviously the system is unstable because one pole is in the positive real axis at plus 1. So the system is unstable. So so we try to stabilize it using unity negative feedback. Once again, the same block diagram, right? So, but now the only difference is that we have 1 by s square minus 1 as a plant transfer function. And then we have the reference input. We have negative feedback. We have unity negative feedback. So the feedback path transfer function is 1. Then we have the error signal. And then we have the controller transfer. Okay. So as we discussed, by and large, okay, typically, okay, it's based on experience, one starts with, sorry, not Kp, but proportional control. Okay, so one starts with P, then one tries out P and PD, then if it doesn't work, we go to PID. Okay, so we always, as a design rule of thumb, right, we start with the proportional control and we see whether we are able to solve the problem using proportional controller itself, right? Then we stop there. So, like what we did in the previous example. So, in this example also, let's start with the proportional control. So, C of S is Kp. So, the forward path transfer function G of S is C of S times P of S. It is Kp times S squared minus 1, right? Pretty simple. And since we have unity feedback, H of S is 1. Okay. Now, you and I know that the closed loop transfer function is G of S divided by 1 plus G of S H of S, right? So, we can see that the process is sort of like very standard, right? Once you and I get practice, it becomes a very standard process. So G of S is 1 by Kp by S squared minus 1. In the denominator, we have 1 plus Kp by S squared minus 1 because H of S is 1. So if we take the LCM and then cancel off the common factors, we get Kp divided by S squared plus Kp minus 1. Okay. So what is the characteristic, closed loop characteristic polynomial? It is the denominator polynomial of the closed loop transfer function. In this example, it is S squared plus Kp minus 1. So consequently, the closed loop characteristic equation is S squared plus Kp minus 1 equal to 0. Okay, so this is the closed loop characteristic equation. So we work with this now, all right? So if we simplify this, we get S squared to be equal to 1 minus Kp. So this is a second order polynomial, but there is no S term here, right? So that's why we are able to process it much simpler. Now, if we take square root, the closed loop poles are going to be S equals plus or minus square root of 1 minus K. Okay, so that's what we will be getting. Okay. Now, things become interesting, right? What happens is that, like if we look at, the ranges of KP, and then like figure out what will happen to the closed loop poles, right? For this particular system, right? We see something very, very interesting, right? What are the observations? We see that, like when KP is greater than 1, okay? So let's consider 3 ranges: KP greater than 1, KP less than 1, and KP equal to 1. If KP is greater than 1, what can we say about 1 minus KP?
It will be imaginary number, sir.
So 1 minus KP will be negative. So we are taking square root of a negative number. So the closed loop poles will be on the imaginary axis, right? J omega axis. And we don't want that, right? Because see, you don't want poles on the J omega axis at all, right? If you and I want to design a proper system, please note, if for a given plant, if poles lie on the J omega axis, which is beyond our control, we studied that, it is critically or marginally stable, right? If there are non-repeating poles, for only select inputs, the output becomes unbounded. But when we design closed loop control system, you and I have to design a proper control system, right? Such that all closed loop poles should compulsorily lie in the left of plane, okay? When things are under our choice, we cannot have closed loop poles on the J omega axis, okay? Simple or otherwise, okay? So obviously, you and I don't want closed loop poles on the J omega axis. Then, if KP is equal to 1, 1 minus KP will become 0. Then it is even worse, right? Because closed loop poles will be repeating at the origin, S equals 0. So it is automatically unstable. Okay, we don't want that. If KP is less than 1, what happens? 1 minus KP becomes positive. So we take the square root of a positive number, then one root will be on the positive real axis, one root will be on the negative real axis. And that is also bad, right? Because one root on the one closed loop pole on positive real axis means the system is unstable. Okay. So what is the lesson that we have learned, and what is the conclusion? That there is no value of KP which will stabilize the closed loop system. So consequently, this plant or system cannot be stabilized using proportional. Okay, so I hope the question is clear. Okay, so as I told, typically we go in this direction, right? We start with proportional. We see whether it works. In the previous example, it worked. In this example, it did not work. That's okay. It's not necessary that proportional control should work in all the cases. Not at all necessary. Okay. We just start like that. Okay. So now that we have ascertained that proportional control is not going to stabilize this closed loop system, we go further. Let's look at PI. So we go and look at PI controller. So by now, I'm sure all of us have got a hang of, like what is the step to follow, right? So what we do is that for PI control, as we know, the controller transfer function is Kp plus Ki by S. So this can be simplified as, if you take the LCM, Kps plus Ki, the whole thing divided by S. Now the forward path transfer function G of S is C of S times P of S, which is going to be Kps plus Ki by S times 1 minus S squared, 1 by S squared minus 1. So we get Kps plus Ki divided by S cube minus S. How did we get S cube minus S? In the denominator, we have the product of the two terms, right? S and S squared minus 1. And that becomes S cube minus S. Okay, so that's how we get S cube minus S in the denominator. So the closed loop transfer function is G of S divided by 1 plus G of S equals S. So G of S is Kps plus Ki divided by S cube minus S. And then denominator, we have 1 plus Kps plus Ki, S cube minus S. So we take LCM, we strike off S cube minus S in the numerator and the denominator. We end up with this. The closed loop transfer function for this system with a PI controller comes out to be Kps plus Ki divided by S cube plus Kp minus 1 S plus Ki. Okay. So now we observe that the closed loop characteristic polynomial is this, right? It's the denominator polynomial of the closed loop transfer function, which is s cube plus kp minus 1s plus ki. It is a third order polynomial. So the corresponding closed loop characteristic equation is s cube plus kp minus 1s plus ki equals 0. So obviously there are three closed loop poles and two parameters, right? kp and ki. So of course, please neglect this green text for now. We are going to conclude it after some discussions. At this point, you and I do not know, right? What to do, how to go further, because we have a cubic polynomial or a third order polynomial. We have three roots, right? Which will be the closed loop roots. And then you and I need to figure out under what conditions on Kp and Ki will all the three roots lie in the left of complex. Okay, so the question that that we asked, if they exist, find regions of Kp and Ki that would ensure that all three closed loop poles lie in the left of complex. Okay, so that is the problem that you and I are facing now. Of course, it is not mandatory that like the solution should exist. That is why we are writing if it exists, right? If it exists, please find ranges of Kp and Ki that will ensure that all the closed loop poles in this particular case will lie in the left of complex. Okay, and in general, a polynomial with all the roots in the left of complex line is what is called as a Hurwitz polynomial. So a polynomial is called to be Hurwitz. So one, it's a polynomial one in which all its roots have negative real parts or lie in the left of complex. Okay, so now the question becomes, how do we proceed, right? So we have come to this cubic polynomial and a third order closed loop characteristic equation with a PI controller. We have we want to figure out what all they exist, with which the polynomial will become Hurwitz, or all the three closed loop poles will lie in the left of complex. Okay, so we are going to learn the corresponding general theory in the next class. So we will conclude today's class with this question. So suppose you and I consider an nth order polynomial. Okay, so which is given by this a naught s power n plus a1 s power n minus 1 all the way till a1 an minus 1 s plus an. Okay, so this is an nth order polynomial. N can be any positive. Okay, so in this example which we considered, n was 3, right? So here in this example, n was 2 because we got a quadratic equation. The first example, n was 1. Okay, so we consider any nth order polynomial d of x, which is of this structure. The question is, how can one determine the distribution of roots of this polynomial without actually calculating them? So this is a very interesting problem, right? See, for closed loop stability, we look at the denominator polynomial of the closed loop transfer function, right? Which is the closed loop characteristic polynomial. You and I do not want to solve the closed loop characteristic polynomial. We want to figure out for what values of the controller gains the closed loop poles, which are the roots of that polynomial, will lie in the left of complex. That's all we want. So is there a method through which you and I can figure out when, if at all it exists, the roots of a general polynomial will lie in the left of complex plane. And also in general, what will be the distribution? That is, how many in the left of complex plane, how many in the right of complex plane, how many on the imaginary axis, and so on. Okay. And the point is, like we also, look at this particular, general case because it will help us in control design. That is, we will be able to figure out the ranges of controller parameters, which will, if possible, make the closed loop characteristic polynomial as Kurzweil's. Then we have closed loops. Okay? So we will look at the corresponding theoretical idea in the next class. Okay? So what is called as a Raoult's gradient. Okay? So we will look at it in the next class. So in today's class, what we have done is that we have done the exercise problem where we have converted the performance specification into regions of, in a subregion of closed loop poles in the left of complex plane, so that we achieve both closed loop stability and closed loop performance, right? We figured out how to go about the entire process. Okay? So in the next class, we will continue how to figure out the answer to this question, and then we'll come back to this example. Okay, so I have already written the solution in green color font, but we'll figure out how to get to that green color font in the next class. All right. Okay. So now open for questions and discussions.
Sir, I have a question. Sir, we have just seen one equation which is PS is equal to S minus PS is equal to 1 divided by S minus 1, right, sir?
I'm sorry. What is it?
So
Can you repeat, please?
plant transfer function is 1 divided by S minus 1.
Yeah.
And,
One.
and we have tried to stabilize a system by using some proportional, I would say, like proportional control system, and we have got something. Got some criteria that if KP is more than 1, the system will be stable, right, sir?
Okay. Yes.
Now my question is that, sir, suppose if I have a equation like 1 divided by S minus 100 or 1 lakh, something like that. So since that inherently the pole will lie much on the RS side, like on the real axis, the pole will lie on 1 lakh or maybe whatever number I select. So which is easy to control, S minus 1, the pole which is nearer to origin or very far from the origin in that sense.
No, see, in this particular example, let's generalize this example, right, based on your question. So I can generalize the example as plant transfer function is 1 by S minus A, right, where A is some number, real number greater than 0. Okay. So I have chosen A to be 1. You are saying A is 1 lakh, right? So if you repeat the same problem, you will see that for stability, KP should be greater than or equal to greater than A. Okay. So if let's say you have a system for the sake of argument where A is 1 lakh, you need to choose KP to be greater than 1 lakh. That's it. Then you will have closed loop stability. Okay.
So that means, sir, what I mean to say, what my next level question is that if KP value is like 1 or like 1 lakh in that sense, what is the implication on actuator or any system like design in that sense?
So that will come later. See, I think Roshan, you built a hypothetical example and I answered that. Okay. Point number 1. Because you and I don't know what will be the value of A. Right? I built a hypothetical example, A to be 1. You built a hypothetical example, A to be 1 lakh. Right? So you and I have now learned that if KP is greater than A, we have closed loop stability. Now, whether we will have an actuator in practice which will realize this control input is the next question. That has to come later. Okay, this is the first step. So what I mean is that once we design a controller, we do closed loop simulations. Okay. So let us say by doing closed loop simulations, you plot the control input U of t with a C. Okay. Let us say your actuator capacity is some 100. Like I'm just using a round number. And by extensive simulations, always your control input is within 100, then you are okay. But if you're during simulation, your actual control input with this KT being 1 lakh goes beyond the capacity, you need to change the actuator, right? So there is no other way, right? So all those considerations will come later, like whether you will have an actuator to realize the control action that you are seeking. That is the next step. I hope that becomes clear, right?
Thank you, sir. Thank you.
I hope that answers your question.
Yeah, of course, sir. Of course. I got the intent. Thank
Yeah,
you, sir.
yeah. Any other questions?
And sir, one more question I want to ask you. Like,
Uh,
we have discussed about two functions where the current function was like the order of one, and second we have gone for a second order system like s is equal to s square,
correct,
or
correct,
maybe it's given that sense.
correct.
So practically, sir, like I want to understand that which type of system is difficult to control, like a system which has the like characteristic equation having more order, or maybe like simpler order in that sense.
So, there is no generic answer to the best of my knowledge, Roshan. But however, see, why are you and I considering first order and second order systems during class? Because they are the ones which are tractable using pen and paper. We started with the 10th order system. Let's say there is a 10th order system in practice. We started with a 10th order polynomial. Let's think about how complex the algebra itself will become, right? Then we won't understand the intuition, okay? So that is a practical reason why I have started with the first order and second order system. Point number one. Now, coming to your question on which will be difficult to control, once again, there is no generic answer, right? Because let us say you have a 100th order system, but you have all the poles in the left of complex plane, it may be easy to control. But let's say even if you have a fifth order system with one pole in the right of plane, a couple of poles on the imaginary axis, and so on, right? That may prove to be difficult to stabilize. Okay. So the answer to your query, my answer to your query would be that rather than the order of the system, I would be looking at what is the like distribution of the open loop. In other words, how many open loop holes do I have in the left of plane? How many open loop holes do I have in the right of plane? And how many open loop holes do I have on the imaginary axis? Like that will in fact dictate how tough the problem is going to be or how easy the problem is. Okay. So the more open loop holes lie on the imaginary axis and in the right of complex, stabilizing the closed loop system is going to become more challenging. Okay.
Amazing, sir. Thank you so much.
Well, right.
Sir, am I audible?
Yes, please. Yes, please.
My question is a bit elaborate, and maybe if it is not relevant right now, you can answer. That's also the case, but just a doubt. Sir, the equations that we are giving for this integral controller as well as the derivative controller, I'm just trying to phrase the equation again. For example, if u of t is ki into integral of 0 to t e of t dt. So that is for an integral controller. And similarly, for a derivative controller, u of t equal to kd into de of t by dt. That is one of the case. So these two equations are there. I just referred another book wherein if I have to have a PID controller, the control signal u of t is given by k into e of t plus k divided by ti 0 to t integral et dt plus k into td det dt. So my only question was this ti and td, those are the time intervals for which you're going to integrate and the time intervals for which you're going to use for the differentiation as well.
Okay.
Correct?
Okay. Okay. I'll let you complete the question, then I'll give the answer. Okay?
Yeah. So my question was this k divided by ti is what is coming as kt, or how we are defining the proportional constant, derivative constant, and integral constant.
Okay. So what it is, I think, Prem, right? I will take a couple of minutes to answer this question, right? I hope that's okay, and I hope you will not be late to your next class, right? So,
No problem, sir.
right?
Please.
In fact, if you look at that, see, I didn't use that notation, Prem, point number one, because this is not a course on control theory. Okay, it's applied to automotive systems, right? So I think I would have discussed this in my control systems NPTEL course, right? The link which I share. So typically, one could essentially do this, right? Which is what I did, right?
Yes, sir. Correct.
Right? And what you are saying in some textbooks, they
Yes.
will write Ki to be Kp by Ti,
Exactly.
right? And Kd to be equal to Kp times Td,
Yes,
dAd,
perfect.
right?
Yeah.
And then what will happen is that they will take Kp out of the thing.
Yes,
It will
perfect.
become 1 by Ti, 0 to T, e power tau, d tau, right?
Yeah, correct.
Am I correct?
Yes, sir.
Okay,
Yes, sir.
very good. So there are physical meanings of this Ti and Td. Okay, so Ti is what is called integral time. Okay. All right, and Td is what is called derivative time. These are the names which are typically given to these two parameters, and there's a physical connotation between for Ti and T. Prem, am I audible?
Yes, sir. Yes, sir. Very
Okay.
clear. You're coming to the point. I'm able to understand. Yeah.
Yeah. So this is what is called as integral and derivative time. Why are they called the way they are? I leave it to you as an exercise and tell me next class. Okay, then we will discuss later. And I think, see, these are giving me good ideas. Okay, like I think these, I'm happy that your batch is asking all these subtle, you are referring to other references and asking me these subtle questions, right? Which are important. And I think that gives me an idea of using these in exams, right? So I hope all of us can agree that some problems in your exams can come from these questions where you figure out and then you come prepared for the exam. Is it okay?
Sir, the entire batch is going to kill me because of this.
No. See, I think these are important, Prem. Like, but I will help you the answer, right? It's not that I'm asking you to go and do it, right? So see, it's important to ask questions. That's how we will learn. See, if I know the answer, I will tell. If I don't know the answer, I will tell I don't know. Right, and we will learn together, right?
Yes, sir, of course.
In this particular case, I understood what you are coming to. That's why I'm telling you this. Why did I not do this? If it were a course on control theory, I would have taught you this. Okay, this is a course on automotive control. That's why I stopped here. Okay, I hope my reason is clear, right?
Clear, sir. Yesterday we were just discussing some practical examples.
To have practical connotations. Okay, so that is why some people will formulate PID in this way. So please find out what is the physical implication of or physical meaning of PI and TD. All right. Okay. And I maybe I will give you some example problems which will motivate the practical implications. Okay.
Yes, sir. Clear. Thank you so much.
And they will come in your exam. Okay. Yes. I hope Arunachalam, that arrangement is fine. No,
Yes, sir. Yes, sir.
Okay. Because I always need to check with our leader before doing anything. Right? So yeah. All right. Any other questions?
So one more question in continuation to what Prem asked. One of the point that was mentioned was when the settling time changes with respect to reduces with respect to.
Keshav, if you want, I can phrase the question. I have noted it down.
Yeah, please. Yeah, please.
Sir, the statement was that damping increases with increasing derivative time, but decreases again when derivative time becomes too large.
Why is that? Because if that makes some presupposed assumptions, Raymond Kessler. If you derive the closed loop transfer function and take the dominant dynamics, you will see that effect. Okay, because there is a relationship between, see, ultimately the numerator polynomial of, the denominator polynomial of a dominant second order system is s squared plus 2 zeta omega n s plus omega n squared, right? So when you design a PID controller and you take the dominant dynamics, like the corresponding transfer function, you will see that, Ti, Td or Kd, Ki and all will be related to zeta and omega n. And that is the context in which those statements are made. Okay?
Maybe right now it is going over our
Yeah.
head. We will try to
Take
understand.
some time. Don't worry
Yes.
about it. Right. So as we keep on reading more, we will understand together. And whenever you encounter such examples, also you can write on a sheet of paper cleanly, scan it and send it to me so that I can also look at it and I can give you my opinion. Right?
Sure. We'll do that.
Yeah, I do understand that depending on the reference that you are looking, which reference are you looking at?
Sir, there was one text from, I think it was from Caltech University website for PID control.
Yeah, so depending on, see, there will be a lot of premises behind these statements.
Understood.
What you and I need to understand very clearly. So without any data, I am giving you a guess. So what will happen is that for any arbitrary system, right, you take the dominant dynamics, Kp and Ki will influence zeta and omega n, because the denominator polynomial of the dominant second order system is this, right? So that's why people make those statements, right? So
maybe, sir, to give better context, we will tell that there were some graphs given wherein TD value was initially we say 0.1 and then TD became 0.7 and then TD became greater than 4 or something. So in that case, how the waveform was behaving, they have given an example and saying that, see, when TD is going beyond a particular value, it really doesn't really damp the case like that.
So see, to give an intuitive answer, see, derivative control block is Kd times S, right? So you write it as Kp times TdS, right? So this is a first order polynomial that will come and affect the 2 zeta omega n component. Okay, so you see that TD has an implication on zeta and omega, right? So if I can make a sort of like a very intuitive correlation. Okay? Yeah. So
Noted,
you can
sir.
turn the specific example or situation and show it, send it to me. I can look at it and get back.
Sure. Yeah.
And did you figure out how the derivative controller is realized in Simulink and MATLAB?
Yes, sir. There was one equation which was given in the MATLAB website, which had a denominator for filter constraints or something related to that.
1 by S?
Yeah.
TS plus 1.
Yes, TS plus 1. Yes.
Okay. Why? We will learn the answer as we go along. Okay.
Sure.
So we are going to learn all those answers as we go along in this course, right? So that you and I are, to the best possible extent, we learn whatever is important, which will prepare us for practice. Okay. So once again, as I told, from past today for automotive control design. Okay, there may be more. I am also learning, right? But then, whatever I know, I am going to convey. But I am also going to share a lot of subtle points which we may not openly find in resources, online or textbooks, right? Which comes with experience, right? So we will learn all these things, right? I will demonstrate to you why we put the TS plus 1 by TS plus 1, and that has to do with that noise attenuation, right? I showed you one limitation of derivative control, right? Amplifies low amplitude, high frequency noise. This 1 by TS plus 1 acts as a low pass filter. Okay? That is the preemptive answer. Okay?
Thank you so much, sir. Yeah.
I think
yes, sir. Today everybody is present, sir.
Everyone is present, is it? Okay. I will mark everyone as present.
Okay.
My only constraint is that next Monday, actually, as I told, till next Tuesday, I'm on leave.
Right, sir.
I didn't want to miss the classes. That's why I'm teaching. I'm continuing teaching even my regular classes online.
Right.
Next Monday, I will be completely unavailable.
Okay, sir. Okay, no problem, sir.
Next Monday class we will not have. Okay, Tuesday onwards we will continue. I hope that's fine with everyone, right?
Yes, sir. Yes, sir. Yes. Thank you.
All right. Okay. So thank you all. So we will continue next Tuesday evening. Okay. Fine.
Thank you, sir.
Thank you. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye bye.
Thank you, sir.
Thank you, sir.
Thank you so much.